Okay, still morning here. Good morning, everyone. So we will start our lecture today with Dr. Tri. So it's still about MCMC. Maybe it's more, I don't know, more practical to astronomical data, but I don't know. Let's see what Dr. Tri will tell us about the MCMC. Okay, maybe Dr. Tri, you can start your presentation.
Okay. Yeah. Thank you. Thank you, Anton. And hello again, everybody. Good morning. It's good to see you again. And I hope you still have the energy to talk about MCMC. Today, we're going to discuss some implementations of MCMC and what we can do with it in practical terms. So we're not going to talk about the basics all over again. Most theories about MCMC. But however, I'm going to talk a little bit about Monte Carlo methods in general, if it's okay with you. Can you see the slides?
Yes, you can see it.
Yep. Okay. Yeah. If I move the slides, you can also see it. This one's page 2. Yeah. This is page 2. Can you see the slide?
Yes.
Yes.
Okay. Okay. So right. Yeah. So I'm here. I'm going to talk a little bit more about Monte Carlo methods in general, and not just Markov chain Monte Carlo. So MCMC is a more broader is a subset of broader terms called Monte Carlo methods, and they basically Monte Carlo methods are used to generate to make use of random numbers. So it's not only generating random numbers, but it's also how to use it to do something with it. So that's why Monte Carlo methods is used for data simulations, and it's also heavily used by physicists to generate particles in computer simulations, and also to compare between models and their observations in large accelerators like CERN, in Large Hadron Colliders, for example. So they use Monte Carlo methods heavily, and I first time I'm dealing with Monte Carlo methods was during my PhD, where I took topics in astroparticle physics. So that has a high energy physics basis. So there's a lot of Monte Carlo stuff there. So I have to learn how to generate random numbers and how to use that to sample functions and things like that. So MCMC is just one class of it. So yep. So that's the idea of MCMC. It's basically just to generate samples that can approximate of a probability distribution function, and also it is used to perform high dimensional integration. So if you have a multivariate functions here, and we want to integrate it over a lot of dimensions, 100 dimensions or whatever, it'll be impossible to use normal quadrature techniques, because there's 100 dimensions, and we have to go all over the dimension and then calculate all the values. That's just impossible. So that's why Monte Carlo methods developed. It's basically to calculate an integral. So that's what Monte Carlo methods are. So now here's the plan. We're going to discuss random number generations, and we'll discuss PDF a little bit. Just a couple of slides, I promise, and then we'll talk about several sampling methods that's in the market, and then we'll see what we can do with it. Yeah, random numbers is the important thing to note is that if you use computers to generate the random number, it's actually not true random. So it's actually what you call a pseudo-random numbers. So it's basically use a certain mathematical techniques that I'm not too familiar with, but it's actually there's a mathematical sequence to generate random numbers, and there's a lot of algorithm. One of them is Mersenne twistor. It's usually used by a lot of algorithms. So if you use NumPy, for example, NumPy to generate random numbers, almost always use Mersenne twistor to generate it. So they're not, even though they're not truly random, they're pseudo-random, but they're enough for scientific purposes. Don't do it for cryptography. You might come to trouble. So you have to use two random numbers that usually generated from natural phenomena. So we're not going to talk about it. Yeah. So remember what PDF? This is basically the likelihood of finding particles or values. You've seen a Gaussian distribution. It's in fact the same plots that I show you. Yeah, so PDF it has to be normalized. Otherwise you can indicate it by star. So it has to be normalized to 1. So, here's a trick to generate. You probably have used it. There's a trick called Box-Miller transform. So this is how we do it to generate normal distribution. So, and you can always generate normal distribution with any mean and scale by using this trick. We generate a random number from a standard Gaussian, which has 0 mean and single standard deviation of unity. And we do this, just add the mean and multiply it by the standard deviation. You get Gaussian. But computers can do that these days. Yeah, this CDF, and we encounter this once more in some of the methods. CDF has to be integrated from -infinity to a certain point. This is a CDF of various Gaussians. Right. So here's the first method that we can try to sample a distribution. So if we have a PDF that we can easily calculate, it's CDF. So we know how to calculate a CDF of a PDF that we want to sample. Then we can also calculate the inverse of CDF, right? The inverse of a CDF is called a quantile function. And the result has to be between 0 and 1. It's properly normalized. So here's what we can do to generate a sample. So we generate U from a uniform distribution between 0 and 1. And then we calculate its quantile function. That's a sample that we want. So here's an example of I hope it's here. Yeah. Right. This is a Plummer model. So it's usually encountered in galactic dynamics. So if you're unfamiliar with it, so it's a model that tells the distribution of a star in a globular cluster. So this is the Plummer distribution at the bottom, and this is the CDF. The Plummer model is an analytical function, so, and we can easily integrate it to get a CDF. So now we're going to sample from it. Yeah. So can you see animation? It's moving. So it's just so it's generating a random number here between 0 and 1, and then we use the inverse of the CDF to get that position, to get the position of X. So over time, it will approximate the Plummer distribution. And that's it. That's how it works. So this is a very easy way to approximate a function if it's, as long as it's integrable, and we can calculate its CDF. We're going to see it again. And it's also very useful if you want to generate a globular cluster to simulate cluster. Yeah, so as I mentioned before, the problem with inverse transform sampling is that the function is able to be analytically integrated and easily inverted. So it has limited applicability. The advantage is it's very efficient. So there is no rejected point. So everything is accepted. So one way to work around is to interpolate the CDF. If it's analytical integration doesn't work, so we have to define a grid of points. So as you can see, it has limited use, but nevertheless it's very advantageous if you know how to work around it. Right. So now the next method is called rejection sampling. So now we use what we call a proposal distribution, from which we can easily do samples. Let's say using inverse transform sampling, or using generating from a normal distribution. The thing is, the proposal distribution has to completely cover the target distribution, the distribution that we want to sample. So for example, here we have a function here that we want to sample. This is our proposal distribution, and if we multiply it by a constant, for example, it has to be larger than the target distribution for all. So it's just quite easy. So first we generate X using this proposal distribution, and then we evaluate these quantities. And then we generate a number between 0 and this value. The proposal distribution multiplied by constant. And then we accept the sample. And then we accept the sample if U is less than this function. So here's another example. Oh, okay. All right, then just show you the whole stuff. Right, so this is the function that we want to sample. It's a bimodal function in the blue, and the proposal distribution is just a constant. Yeah. It's very easy to sample from a uniform distribution. Just generate the values between this range, between -5 here and +5, and you get it. So if we generate a point here, it will be it will be more like it will be less likely to be accepted than if we generate a point here. So that's the point, right? So as you can see, that's the point. Now, as you can see here, this is the number of samples that has been generated, and this is the rate of acceptance. Sorry, or maybe this is actually the number of samples that are accepted, and this tells us between all of these points that is generated all over the place. What is the percentage that got accepted? Yeah, so here red because it's generated here, because it's generated here, because the random number that's generated here is less than this function and this value here. So that's why it got accepted. So if we move back a little bit here, we generate a point here at this x position, and then we generate a point between here and here, and here, because this is higher than this value here, then it got rejected. So that's the idea. So just continue on until we find it. So yeah, so like here it got rejected. Yeah, it's just basically just generating samples all over the place. That's very good. So as you can see, if the proposal distribution looks very much different than the target distribution, then we might get a low acceptance rates. Like here, in the end, there's only like 25% of the samples. So we generated about 1,000 samples, but actually there's a lot more because only 25% of whatever is small is generated. Maybe I don't know, 7,500. Yeah, that's this is 4,000. So actually there are 4,000 samples here generated, but only 1,000 got accepted. So that's a problem. Yeah. So how do we improve it? Well, we find a proposal distribution that looks better, that closely resembles the target distribution. So let's see whether that works. See, so now we use a Gaussian, and as before, it completely encompasses the target distribution here. So sampling from a Gaussian is also quite easy. So as you can see now, we have a higher acceptance rates. So only 50%. Right now, only 50% of the samples are rejected. So that's the trick in rejection sampling. So as you can see, we must see what the target distribution looks like, and then think about what's a good proposal distribution that we can use to approximate this. Now this can be a problem in multi-dimension. So this is usually used only in 1 or 2 dimension function. Which brings us to MCMC. So we use MCMC generally to sample from highly high dimensional functions. So we already discussed about what is MCMC before, by Professor Feigelson. So basically, it's just a series of random variables. You can treat it like imagine it's like a time series. And then we generate samples at a different t, at a different phase. But the current sample, it doesn't depend on the aggregate of the previous states. It's only depend on the current state. So the next state will only depend on on the current state. It doesn't depend on all of the previous states. So that's the thing. So you already seen this expressions here. It's the probability to get the next state given all of the other states is actually just this. It only depends on the current states. So that means the probability to move from one state, from the current state to the next state, it's only depend on the transition probability. The probability to move from one state to the next. And it has to be independent of the time, because we have to imagine this as a sequence. Yeah, I hope that explains what is it, what Markov chains is. So we combine the idea about Markov chain, in which we incorporate a transition probability from one state to another, into the offer multiplier methods. So now we'll discuss two MCMC methods here. It's very popular. The first one is called metropolis hasting. And yeah, this is very popular in astronomy. Affine invariant and sampler. It's by Goodman and Weir, 2010. Yeah, so we use again, we use a proportional distribution that describes the probability to move from one state to the other. All right, so we generate a sample from this proportional distribution, and then we compute this, which is basically the odds ratio, like in Bayes factor or in hypothesis testing. This is yeah, so this is the odds ratio between the current state and the next state, and then this is the transition probability. So it's just the proportional distribution at the next state, at the present state, and then the proportional distribution at the current state. And then if it's larger than 1, then we accept it. Otherwise, we do the sequence. We have to calculate a uniform distribution, and then we accept only if A is larger than U. Right? So if it's accepted, then this is our new position. Otherwise, it's stay at the same place, right? And then it only moves until it found a better new state. Right. So if our proportional distribution is symmetric, then the ratio is always 1. Now, so here's another example. There it is. Right, so we use a Gaussian as a proposal distribution for moving from one probability to the next. Make it a little bit slower so we can see where is it being generated and whether is it accepted or not. Okay, so you can see we see there's a lot of peaks here, and sometimes here. It's because it got stuck there, and then it keeps, and then it refuses to move. So that's why there are more points than the other. Okay, let's skip to the end. No, there's no plot twist in the middle. So yeah, so that's metropolis hasting. So as we can see, this will heavily depends on the width of the proportional distribution. If it's too narrow, it can get stuck in the local in the same spot, over and over again. So it's going to be difficult to explore various areas. If it's too wide, we might not be able to generalize it into the target distribution. So in here we have to carefully think about the proposal distribution. And again, that's a lot. Sometimes it can be difficult, especially if it's multidimensional, things like that. All right. So yeah. So I already said that. So here's a way to evaluate whether a chain that we're running. So we usually call MCMC run a chain. So one sample to the next. That's usually called a chain because it forms, a chain, as the name suggests. So if we want to know whether a chain has converged to the target distribution, then we can use a lot of convergence diagnostic. That's a lot of people. Professor Feigelson has already talked. There's a lot of ways to do it. An example is to calculate the autocorrelation, which is basically the distance, the average between one sample and the other. I think this is a typo. So there should be an equal sign here. So if there's a low autocorrelation time, that's the sample is already independent of each other. That means it's already converged to the target distribution. So another concept is what we call a burn-in. This is not really contentious, but some people like to contest this. But it's common practice. So usually, samples in the first few steps, they're still correlated with each other. So they still retain the initial distribution of the proposal distribution, whatever. So and then they'll move, and then we'll generate more samples. Then the sample will be less correlated with each other, but they will only depend on they already approximate the target distribution. So the first few samples are usually discarded. This is called the burn-in. Now, how many samples to be discarded? That's usually what people debate about. You can calculate the variance of the sample. If it's very high, that means it's not yet correlated. If the variance already stabilized to a certain point, that means the variance that means it's already approximate the target distribution. But it can also actually be that it got stuck in a local in local area if the proposal distribution is bad. So be careful about it. I usually just look at it. It's already close to a certain value. Okay, this is how many samples that I have to discard. Right, and finally, we'll talk more details about the affine invariant ensemble sampler. So yeah, so we've seen all of the previous methods. They all depends on the proposal distribution. So this is what they call a non-adaptive. So the step size, it all depends. It's all totally driven by the proposal distribution, and it doesn't really change over time. So we actually want to find something that we can adapt to the target distribution that can evaluate what is the value. Is it high probability or low probability? Where should I go? So this is what's proposed by Goodman and Weir in 2010. And as you have heard, it's called there's a popular implementation called MC. It's by Foreman-McKee et al. And it's used by a lot of astronomers everywhere. Everybody use MC, but that's not the only implementation. There's a lot more. Yeah, it's called. I think if I remember correctly, they used to call it MCMC hammer in the past. That's why it's called MC. Yeah, that's how it got called. You probably don't know MC hammer. It's MC hammer. It's a rapper from the 80s. He has baggy pants. Yeah, Google it. Yeah. So where was I? Yeah. So the affine invariant sampler. It doesn't use any proposal distribution. So as you can see, it uses what we call workers, an ensemble of workers. The number can be it can be predetermined. It's predetermined. So between, I don't know, 10 workers, 100 workers, 1,000 workers. So it can be a lot, depending on the power of your of our computer. And each worker is the parameters, is the sample. It's a factor. It's a factor if it's in multi-dimension. So if the function that we want to generate sample from has 5 parameters, then, and if we have 1,000 workers, then it's 1,000 by 5 matrix. And it's simultaneously evaluate the parameter space, and then they will update its new position based relative to the other position. So imagine it's like a worker is like a bunch of search team, right? And exploring a mountain. So each worker is on a different position in the mountain, and then each knows the height of its. Each individual workers know the height where it's located, and then they will share this information between each other, and then they all move to a position where they have a higher place. So that's the idea. Yeah, so this is an illustration by from Goodman and Weir. I forgot where it came from. Yeah, suppose we have a K worker. So, and then at each iteration, we pick for each worker. So we repeat this movement for individual worker. So here's a worker. It will pick a random other workers. Let's say here. And it will draw a line between these two workers, and it's going to propose a move here to this point Y. Right? And, but the distance between this worker that we're evaluating to the new point is it's a stretch by a certain constant Z. So that's the idea. Then we repeat the whole process for all of the other worker. And Z is not the size of the stretch. This is why it's called a stretch move. At this phase, it's not constant. It's variable. Right? It's the number of Z. The size of the stretch is randomly drawn from this distribution. This is very easy. It's very easy to draw from. So, but the Z has to be between this range. So let's say if A is 2, it's between half and 2. So either the distance is make smaller by half, or we enlarge it by 2. So it can be half of this or twice of it, but it's random between them. So can change it. Yeah, that's how we do to generate using inverse transform. So I told you we're going to come back to that again. And then now we'll calculate this transition probability, and once again we draw numbers. So as you can see, this is actually quite a simple steps. We can actually implement it ourselves. I even wrote it myself in Java, and I already use it for years. And it's still working nice. Of course, we have to be aware of its limitations. But of course, MC is the more popular package that astronomers use. I don't think you have to write your own package unless it's absolutely necessary. You can just use whatever you need. If it's working for you, then that's fine. But as you can see, it's not a terribly complicated algorithm. In fact, we can actually write it ourselves if you want to. Right. So yeah, because we're talking about MCMC, so I will try to concentrate about that and the whole Monte Carlo methods in general. So, yeah, as I have said, then in general, MCMC is used to sample difficult probability density functions, PDF. That's difficult. What do we mean by difficult? That's crazy shape. We cannot analytically integrate it. Then it's highly dimensional, like you have 100 dimensions, or it's That's usually why we use MCMC. So here's a few that I will cover here. So we'll talk about outlier detection, robust regression with MCMC. And we'll talk about how to infer parameters when the data has uncertainties in 2 axes or even 3. And we talk about how to infer parameters. Right. So yeah. So outlier detections. Suppose we have this funky looking data. There is an outlier here and also here. Now I mark it red because just to show this is an outlier. This is a true outlier. It's generated by a computer. So the computer knows it's an outlier. So I mark it red just so that we know this is an outlier. Of course, when we have real data, we're not going to mark it red just because it looks crazy, because it's out there. So real data will have this also black. So I just show it like this. So this is actually outlier. But anyway, we have an outlier. So how do we do that? So people like sigma clipping. Everybody use it. Sigma clipping is basically we start from using all data and we calculate the residuals. And then if the residuals are more than 3 sigma, then we get rid of the data. And then we use restart the inference, calculating the parameters without the data that are more than 3 sigma. And we repeat that until no more data are rejected. So that's how people do sigma clipping. And there's a function to do that in Python, Astrostatistics. You don't have to write it yourself. The idea is that you just have to predetermine the how many sigmas do you want to reject data. So and sometimes we just manually reject points. I mean this is obviously an outlier. This as well, so you can just probably get rid of it. But they have small uncertainties here. I mean, what is this? So sigma clipping can be arbitrary. I mean, we have to choose the sigma. How many sigma do you want to choose? 3%, 3 sigma, 1 sigma, or 5 sigma? It's and also manual removal is a bit subjective, right? And sigma clipping is it can also be a little bit unstable if we choose if the data, if by including all data it already we already got the wrong results, like here, for example. This is 3 sigma of so the dashed line is the inferred model when all data is included, including the outlier. And we want to use this as an initial values for sigma clipping. If we say 3 sigma, then this guy is already, and then this guys will be rejected, and we're only using this. So tend to be subjective. So what do we do? And yeah, and manual removal is somewhat arbitrary. And the problem with sigma clipping is it doesn't really optimize an objective function. There is no loss function that we want to optimize. We just want to get rid of points. One of the better way is to put it in the likelihood in the model. So our data, our likelihood model, our noise model has to include outlier model. So that's how we treat outliers in a probabilistic manner. Yeah, just explicitly model it. So how do we model it? How do we model outliers? We can use a mixture model. And if you look at other papers, a mixture model has a certain probabilistic motivations to it, other than the fact that we use 2 likelihood function. So we can use 2 models, one for an inlier So data that we think is drawn from the two parameters that we want to infer, and then we have likelihood for an outlier. So data is drawn from somewhere else. So there is a lot of you can use anything, but I like to use Cauchy functions, as we have seen. So it's centered on the two model that we want to infer. It has a width, but it has a broader tail. So we can assume that the inliers are. So we can assume that it could be an outlier. Yeah. Right. So and then we combine this these two likelihood with a mixing factor p here. So p is we multiply p here and then 1 minus p here. Yeah, that's it for the likelihood. So the likelihood for the observing the data that we have, given the parameters and the mixing factor, and also the width of the Cauchy distribution. So we have to infer this as well together with the parameters. We can guess, but I mean, we're already doing multidimensional sampling already. But why don't we sample it as well? So now, if we are using straight model, we have here has two parameters, and here's additional 2. So I just want to make a note here that the outliers that I've drawn here, it's not drawn from the Cauchy distribution. It's drawn from any other distribution. So we're not cheating here. So we use something else to generate the outliers, but we try to figure them out using another distribution just to see that it's okay to use different, because we don't know anything about what's the underlying distribution is. We can only assume. Right. So now, what is the appropriate prior for straight line parameters? Now, if we normalize the data and then we center the data so that the 0 point will be close to 0, then we can probably assume a standard Gaussian. Or we can use a very wide Gaussian, and we can also look at the properties of the data. If you look here, if you just draw a line here, it should be around here, right? So just use probably around 0 with a very wide Gaussian. This should be okay. Now the slope. Now the problem with if you just use a uniform distribution in the slope, it will favor a smaller. It will favor a higher slope than slopes close to 0. It's not really a good assumption to use uniform prior for a slope. So what we can do is we write the slope as the gradient, the tangent of the gradient angle. Yeah, a straight line is a gradient, right? So why don't we actually sample alpha, the angle between the gradient angle, and then we assume a uniform prior in alpha. Now also we know the sign of the gradient, so we don't have to actually restrict the gradient to be between 0 and 180 degrees. So in this case, we can actually restrict it between 0 and 90 degrees. And if you look at it, although it's possible, if there's an outlier, it can be like that, right? So so it's up to you. I think it's okay. I mean, this is probably, I'm probably not making the right arguments. So it's okay to set it up between 0 and 180 degrees. Who knows? Maybe actually this is the better point. This is the better line. Now, what is the motivation to use a mixed model? It's because we explicitly penalize rejecting points. So that's the idea. We want to see compromise. We don't want to reject all points. I mean, if this line here is the better line, that means we have to reject all of the points here. So point rejection has to be penalized. So that's the idea of using a mixed model. We don't want the model to skew from a Gaussian likelihood. So, but we also want to put a lower weight to it. So that's the idea of using mixed model. Right. So what's the prior for the mixing factor P? This is prior in probability, and as we have seen before, a good prior for probability is a beta distribution. So when we are doing point tossing hypothesis. So don't use uniform prior. And we also think about what do we mean by outlier. Outlier is a point that is rare. All right, so it has a low probability to appear. That's why it's called an outlier. Yeah, it's a point that is rare. So it's better to use a beta function that skews toward zero probability. So here's an alternative of a prior distribution, prior for P that use a beta function. We can use a highly skewed beta distribution, or something that's a little bit shallow here. That's fine. I usually like this, the green one. So, but really, it's actually a matter of choice. So don't use uniform distribution. That doesn't really make sense. Now, for the width, you probably have heard about Jeffrey's prior. That's something that we can use if you don't know anything about the prior, about the parameter, what it should look like. We use a Jeffrey's prior, and usually when we're talking about width, some kind of width, then the Jeffrey's prior is usually log. It's linear in log width, like this. So we can use something like this. So the prior for the width is a log gamma, and we should also sample the distribution in gamma in log space. Why? Because first it forces the width to be positive, because log function, if we take the exponential, it will always be positive. And second, it allows a wider range of parameter, a wider range in the parameter. So it can sample from the very small when it's minus, but it can also sample the very large when it's highly positive. But of course, we know this function in log is an improper prior. So it goes all the way. It goes all the way to highly negative value. So set a range. Yeah. So then it doesn't go very small, and it break the computer. So break the limit of accuracy of the computer. Just set up a reasonable range. What do you think with this? Yeah, so we put them all together and then we run MC. So I'm going to give you the code on how to run this, and then we can do what we call a trace plot. This is basically the position of where the parameter is, at every step. So it goes. So this is the position of every walker. So I run it to 1,000 steps, and this is the position of individual walkers here. So now, if you look at it, so here's the first few samples that we have to discard, right? And so this hasn't converged to the distribution PDF that we want to sample. Right? Yeah, so it makes sense to remove the first few samples here, and we just use this one, and we can also thin the sample. So there is 100 walk. I set up 100 walkers, and there is and then there is 1,000 steps. So 100 times 1,000, that's 100,000 samples. And if we remove the first 200 steps, we're left with 80,000 samples. We don't really need that much actually. So I mean, if we just thin it by a factor of 8, then we're left with 10,000 sample. I think that's enough, or even less, like 5,000. Because once it has converged here, however long this continues, it won't increase the accuracy of approximating the distribution. So the accuracy will stay the same after it converges. So we don't actually need that much. But why do we want it? But why do we want to run it for a long time? So it's just to ensure that that the steps they already forget about the previous memory. They already forget about the previous memory. So we run it probably for quite some time. And we don't probably 500 steps already enough. But if we have too much sample, we can actually thin the sample by a factor of 8, for example, by a factor of 10. So we only have like a few representative samples. Yeah, so that's corner plot. So that tells us the covariance between each parameter. That's a histogram, one-dimensional histogram. So this is basically, it tells us the marginalized PDF. Of course, this is a 4-dimensional function. We cannot imagine a 4-dimensional function because we have 3-dimensional beam. So what we can imagine is 2-dimensional, 1-dimensional. So that's why we do this pairwise correlations to evaluate. But if you look at the 1D histogram, this is actually the marginalized PDF. So what is shown here in the top, that's the median of each margin of each 1D histogram, and also the credible intervals. Yeah, I think this is 90% credible intervals, but we can set it up as much as we like. So for however we like. So yeah, this is probably a reasonable number. When they look like Gaussian. So of course, there's a correlation between angle and 0 point. But there's a way to remove the correlation, like normalizing the data. Yeah. So how does it compare? So this is our previous estimate. It's wrong in this part, and also the because it takes this into account, and it tries to get closer to this and this. So that's why it gets skewed towards this. This is a true line, the solid blue line. And now this is our estimate using outlier model. As you can see, this is better than when we ignore them. So now, is there a way to evaluate probabilistically if a point is an outlier or not? Yes, we know the mixing factor. We know that we have a model. So what we can do is calculate the probability ratio. So we have two hypotheses, outlier and the total. So we just calculate this odd ratio, but we have to weight it by we have to marginalize it over all possible parameters. So this is how we calculate it. We calculate this ratio, and then we marginalize over all possible parameters. Now, as we have seen, MCMC or Monte Carlo methods can be used to calculate integral in high dimension. So we can just use the sample that we have gathered in the MCMC run to approximate these integrals. And then we just use the sample to calculate these values, and then we weight, and we take the mean of all the values, and that's our value of the integral. So that's easy. So now, once we got the outlier probability for all of the data points here, anything with outlier probability more than 50% is can be seen as an outlier. So I've marked the points that has outlier probability of more than 50%. Of course, the method is not all perfect. There are several points here that are missed by the outlier identification. It's okay. I mean, this point is already quite far. It's already down-weighted, and this point is heavily down-weighted, so it's not doesn't participate in the inference much. So yeah, that's. But as we can see, we can identify which are outliers, and we can see we get a better results by considering outliers. Don't ignore them. Be them, make outliers part of your model. Don't ignore them. Don't use ad hoc random procedure. Try to model them in a probabilistic manner in the model. So include them. That's probably the takeaway message here. And before we move on to the next topic, I actually forgot to show you how affine invariant method works in 2D. So here's a banana function. It's called the Rosenbrock function. It's usually used as a testing function to test algorithms. So this is our initial point of walkers. I just randomly generated them from a Gaussian distribution in 2Ds. So they're all over the place, but they're in the wrong place. And this is the initial distribution of the walkers, as you can see. They look Gaussian. So if we run them, after a few steps, they manage to approximate this difficult function. The blue is the initial point that we reject. So yeah, there's 200 steps, and we already got a nice distribution function that we want. All right. Yeah, so that's how it works. Yeah. So yeah, that's some conclusions I already talked about. You can read it yourself. Yeah. So for the first point, we have a single value of a mixing factor p. So it's basically, we can view this as an average probability that a point is an outlier under this model. But probably points might have a different mixing factor for each data point, and so we can evaluate them. So now we have, so if you want to assign individual mixing factor for individual points, then it's also possible, and then we include them in the model. So now we have two models for the straight line. We have the width and average width, and also we have as much data point as we have. So we have actually more data, more parameters than we have data, but it's okay. It's we have priors. That's the thing. Priors is a form of regularization that allows us to actually infer more parameters than we have data. And basically, all of these parameters, they will be marginalized out anyway. So we can do that as well. And also another way is try to find another loss function that's more sensitive to outliers. There's a lot of literature about it, like using the Cauchy function. But Cauchy function is a specific form of student's T distribution. So a T distribution is Gaussian. It's a distribution with a mean, with a center, and then it has various degrees of tail. How high is the tail now? And it's determined by another parameters called the degrees of freedom. Now, Cauchy distribution has degrees of freedom of 1, and Gaussian has degrees of freedom of infinite. So Cauchy distribution and Gaussian distribution is actually a form of student's T distribution. So what's the appropriate degrees of freedom? Well, that can be inferred from the data, so we don't have to worry about it. Right. So the second topic is regression with uncertainties of both axes. So sometimes we see this data. It has uncertainties on two axes, right? And it has not only in y but also in x. Usually we only have uncertainties in the vertical axis because we assume that the noise in the horizontal axis is negligible or noise-free. Noise-free is impossible, but we assume it's small enough that they won't change by much. Sometimes it makes sense, but sometimes we have data with two uncertainties. And, for example, if we analyze redshift and distance, and redshift estimation can be flawed and the vertical axis, whatever we want to evaluate, that's also even more crazy. So how to deal with it? And also more generally, what if x and y is also correlated? So here the uncertainties here are in the form of covariance matrix, right? And this is, for example, the 1 sigma area of where the data is lying. Right? If it's here, there's no correlation. So the uncertainties in x and y is here. But if the data is correlated, then we can draw the covariance matrix in x and y. So how do we deal with that? If we just ignore the uncertainties in x-axis, then we get this line, just kind of wrong, right? If we compare with the two values. Some people like to suggest that we can add the uncertainties together like that. So the uncertainties on the vertical axis is the square root of the resultants, x squared plus squared errors in x and squared errors in y. That's just wrong. Then it only enlarge the uncertainties like this. We ignore it. And then now it just enlarged the uncertainties with, and it's unjustified. And remember a couple of days ago, we talked about a geometric interpretation of regression. It's basically least square maximum likelihood assumes that the two a point that we observe in y lies vertically because of Gaussian distribution in one dimension. Right? So that's just a wrong assumption, and also it's still the wrong line. So how do we do that? There is one method. It's called total least square. It's to solve it in a maximum likelihood way. And however, this uses a Gaussian error model. And if you want to try a more general case like non-Gaussian error model, you can try the usual Bayesian way. Write what the posterior looks like and sample it using MCMC if there is no analytical solution. So here's a way to do it. We can assume that what we observe is equal to the two values here that we don't know, plus noise, right? So we can write this. We can write the likelihood to observe x and y, given the two value of x and y plus the noise model with the parameter of the noise model. If it's bivariate Gaussian, for example, then phi is a covariance matrix. Also, we have to assume that the model. We can also assume that the model is deterministic. So y, the two value of y is solely determined by the by the two value of x and the model parameter that we want to infer. So then we can write the likelihood to observe the data given the parameters and the noise model parameters as a marginalization in x and y. And we can write it like this. Now, because y is independent of x in a probabilistic sense, we can separate them. What is the probability of y given x, and what is the prior for x? Now, again, here we don't know anything about the two value of x, where it might lie b, so we can assume a uniform distribution, and we can just say it's somewhere in a arbitrarily very large range between these two values. So the probability is uniform between this range and 0 otherwise. And then for y, we can for the two y we can just assign a deterministic value, because we assume that model is y is only depend on where x to x is like. So it's a delta function. So then we can integrate it. So this is the form, the expression for our likelihood when the two values of x and y is marginalized out. So here's the likelihood to observe a total the data set, all of the data set, so the product, and the posterior is this. That's the prior, and this. So yeah, as you can see, this involves if you have n data, then evaluating the posterior will involve n integration of one-dimensional function. So no, sorry, it will involve n integration, n one-dimensional integration. So and in general, there's no analytical solution for this, so this has to be solved numerically, and this can be expensive, but nevertheless, we can use this method to apply this to an arbitrary noise model. So maybe it's computationally, even though it's expensive, maybe it's make more sense to do this. So here's our likelihood. So it's just a Gaussian centered on the two values of x and y. This is the covariance matrix. That's the uncertainties in x and y, and that's the covariance. Right, so here's where we left off before. This is where we ignore the uncertainties in x in dashed line, and this is the two lines. And we got, well, it's not perfect, it's not spectacularly good, but it's better than when we ignore it. So maybe this has some values. Now the problem is here the uncertainties are quite large. So so that's why it's already difficult in the first place to infer the parameters of the straight line. So, but if we consider the x-axis as well and the correlations, then it works better than if we just ignore them. Right. So that's how to do uncertainties in how to do parameter inference when we have uncertainties in both axes. So now we'll return to the distance estimations using parallax. So we have seen that yesterday. How can we do better? We can include more information. So for example, distance of photometric information will also depend on distance of an object. So how can we do that to improve our distance estimation? So I'm going to use Gaia here as an example. So Gaia will not only measure positions of a billion stars, but it also will measure their brightness in 3 bands. That's what the bands looks like. There's what they call this BP band. It's a white filter in blue, and RP is a white filter in red, and also G band, which is basically white. It's an unfiltered. This is what the uncertainties looks like as a function of Gmac. So as you can see, we expect this to have a millimagnitude precision, but BP and RP can be quite worse, especially blue in the frame edge. This is still simulated data, so this is done when we don't have Gaia data yet. So now our data is the parallax, the G band brightness, and also 3 colors that can be formed from these 3 bands. Yeah, and we want to infer not only distance this time, but we also have to infer the extinction, line of sight extinction, the absolute magnitude, and the color. Yeah, because all of this data also depends on these 3. So it's not only depends on distance, but also it depends on their position on the HR diagram. Yeah, this is why we have to include color and absolute magnitude at the same time, because our prior is an HR diagram, and also because what we observe also got extinction by suffer extinction by interstellar matter. So we also have to figure out how big is the interstellar absorption. So then we can calculate the posterior, this as usual, and the likelihood is still a Gaussian. So F here is what is the forward model, the generative model that transform that predict the two values of this. That use this prediction and then transform them into the data. So from the generative, so there's this function is in high dimension. It transforms all of this parameters into what we observe. So there is a magnitude transformation involved. There is an extinction model involved, and also a galaxy model. So that's the priors. We assume all of them to be independent, distance, extinction, and these two. Of course, we can't assume they're independent because we have a prior for that. It's called HR diagram, right? Scalar magnitude diagram. So stars are not randomly distributed along color and absolute magnitude. There is actually a function that tells us where to find stars in the space. So that's what we use. And then we use extinction map as a prior for the extinction, and we use a galaxy model that I already described yesterday for the distance. So then we use to compute the posterior. We use MCMC to sample this because there are 4 parameters, and then we marginalize over these 3 to get the distance. And then because we're working with simulated data, we can evaluate how do they perform relative to the true distance. So here's summary performance again. This is what we see yesterday. Yeah, as we have seen, the exponential space density it looks very good here, but for terrible poorly measured stars, it has a really high bias. It's better off that we use a galaxy model. And if you use photometric informations, then the bias gets very small, and then the uncertainty is also not bad, and the RMS error here it's also comparable to the Milky Way space density. So what's important here is the bias. It's almost gone for all of the distance being considered. So that's this is what happened if we only look at stars with good photometric information. The bias is even reduced further. And so here we only look at what happens. Before we only look at all stars, but now we look at a subset of stars that has good photometric information. As you can see, it works pretty well. Right, so that's what I think. That's what I can say about MCMC. I hope that helps in deciding whether you have to use MCMC or not. So here's some final things that I have to warn you about MCMC. MCMC is not an optimizer. This is not to find the maximum likelihood or maximum posterior, whatever. It's a tool to sample difficult function. So if it's an optimum value of a function that we want, there are better methods to do that. So if that's what we want, don't use MCMC. Now, and the second thing, if we have a multidimensional multivariate function, marginalized mode is not the same as the maximum point of the posterior. Right? So what's the difference. So the maximum point of the posterior is called the MAP, maximum a posteriori. It's a single parameter. Yeah, it's a single point where the posterior is maximized. So while marginalized mode, it's the peak of the one-dimensional posterior where everything has already been marginalized out. So here, this is a marginalized mode here. It's not necessarily the same as MAP. But, especially if the if the posterior is funky looking. So and sometimes it's a different value. So, and in fact, sometimes they can be located far away, but the MAP is actually outside the credible interval. So be careful in defining what do we want out of MCMC. So, yeah, so that's everything about MCMC for me. So if there's any questions, please.
Okay, thank you, Dr. Chris. So I want to invite you to discuss, ask question directly to Dr. Tri. So we have about 15 minutes before the end of this session. Okay, if there's any question from participants? Okay, I see. Okay.
Nathan, were you raising hand?
Yeah, who is raising hand?
Me.
Okay,
Yeah,
let's go ahead.
Please.
Okay. Thank you for the explanation, Mr. Tree. So I'm curious about MCMC. So I'm not really sure to grasp all the concept, but let's say I have a problem. So we know atmospheric optics more or less. I mean, that's a really old theory and experiment. Let's say I have a light curve of a twilight. And then I want to know actually what is the biggest factors. Let's say, is it the factors of the aerosols or the zodiacal light and stuff? So we don't know exactly. Is MCMC is a good tool to see which factors at that specific time actually dominate? So I'm really curious. Is that a good tool to approach the problem?
Yeah. So that's an excellent question, and it's actually it's a research question. Yeah. So if you want to find if you have data, what's your data gonna be? Do you have all of the parameters like aerosol or?
No, I just have the light curve, so it's just time and then magnitude. That's it. But
Okay,
I
so
know more or less the height of the sun. Yeah, probably from the picture we can more or less see the clouds and stuff. That's the only data.
Okay, so we only have time and brightness, right? Is that?
Yeah.
Yes, and then we want to evaluate what is the most important contributing factor. Is that? Okay, so you might be able to use MCMC if you have a model, if you have a multivariate model that can predict the brightness of the atmosphere. Is it the brightness of the atmosphere or the brightness of the star behind
just the twilight, the atmosphere?
Twilight, the brightness of twilight. Okay, so if you have a model generative model that can predict the brightness of the twilight at a given time, and then you include all of the parameters that you want to infer at any given time, then you can probably use MCMC, because you have this prediction, you have this brightness probably has uncertainties, and then the model move in time, right? So, but it has a certain parameters in the fluctuation as a function of time. So you can include all of the parameters there, and then you try to sample it from the posterior, and then you can see what the prediction looks like. But in my opinion, this is not. You don't have to do MCMC with it if you just want to infer the parameters of the time series model. You can use maximum likelihood, especially if the model is linear. This is probably a good optimizer out there. So, but if you need its uncertainties, for example, you don't actually need you need MCMC to evaluate the uncertainties. So you can go. Yeah, there's. I don't think you have to use MCMC for this case. Yeah. So another way that you can do is if you have other measurements as a function of time, Yeah, so it's not only brightness, but also how big the aerosol content in the atmosphere, for example. That's another parameter. And what else do you want to consider? Like let's say if we have a spectral, line at each time. So you can use another like kernel methods or random forest methods. Now random forest, it can methods like random forest, it can evaluate how big is the influence of one parameter over the other. So that's probably a good tool. But then you have to have other informations other than brightness. If you only have one parameter, that's time. If you only have brightness and time, that's not really useful. But you can use extra trees if you have multi-dimensional data, multivariate data, and you want to know what's the most which parameter that has the biggest influence on what do you want to predict. So I hope that helps. So,
thank you very much. Really.
Basically, yeah, if you want to sample, basically MCMC or any other Monte Carlo method is if you want to sample from a distribution, that's how to do it.
Okay. Okay, great. Thank you very much.
All right.
Okay, thanks, Arifin. So is there anyone here who wants to ask a question? Okay, maybe from me, how to handle about minimum local minimum in MCMC code.
Okay, yeah, this is another difficult question, yeah, and nobody really has the answer, but there are some ways. You know. I will use parallel tempering. You know, so imagine, so it's like when you're creating swords, you know, for metal. So we hit the metal and to a certain temperature. That's the idea about parallel tempering. So we hit the likelihood functions. So we have a likelihood function with different temperatures. That's basically the idea. If you look at the equation, of parallel tempering, it's actually we multiply it by a certain factor, by 5 or by 10. That means the one that's multiplied by 10 will have a higher probability than the one that's will have a wider distribution than the one that's has a lower number, lower temperature. So the one with the lower temperature will be more narrow than the one with the higher temperature, which is very wide. So this allows the states at different levels to explore either a very local region using the low temperature PDF, or a higher and also a wider area using the higher temperature PDF at the same time. And they should be allowed to exchange information between the higher and the lower temperature, and then they should be able to switch place. So then we finally take the one that, and then we have different levels: the one with the low temperature, the one with the high temperature, and then we take the one where it's not heated at all. So it's the target distribution. So we take that. So that's after they're changing information. So parallel tempering is a powerful technique. It has been used to find orbits of exoplanets, you know, or multiple orbits, and to some degree of success. Usually it's also depends on the data, but they usually be able to find very significantly maxima. But sometimes it didn't really help. So once we look at the distribution, at the final distribution after a few days of MCMC run, you still have some values trapped in the local maxima. They're unable to move to the one with a higher probability. So sometimes you can see it. They're still scattered all over the place. So how to do that? You can do clustering. So clustering analysis to identify, to approximate the PDF, and then we can remove points that have lower probabilities. So we have to combine. Sometimes we have to combine them. This parallel tempering and clustering analysis in order to remove clusters that have lower probability. So that's one way to do it. You know? And yeah, people have used it, and they claim, oh, we found 5 planets. Okay.
Okay, yeah. Yeah, thanks for your answer. Is there any question? Your last chance to ask Dr. Kid directly. No? Okay, Lakno, please.
Yeah.
Excuse me, can you hear me?
Yes, I can hear you.
Okay, I have a question about the burn-in phase.
Okay, yeah, burn-in.
And about the data, if we don't want this burn-in phase, if there are any method that can avoid this phase?
Burn-in is a fact of life. You cannot avoid it, you know, unless you are exactly at the, unless your initial positions already exactly match the distribution that you want, or it happened to be in the, you know, inside the area that has a high probability to lie there. It's unavoidable. Your worker will be all over the place, and then they'll try to converge to the shape of the PDF. So you cannot avoid it. You know, that's why, you know, that's why people talk about the burn-in, how many to burn in, how to evaluate which point to discard efficiently, you know, by this many criteria to assess it. There's this autocorrelation time, there's this Gelman-Rubin test, whatever. So it's unavoidable. So you have to discard the first few steps because they're not still. They still remember their initial position. They're not yet reached Markov chain. That's probably the idea.
Because I have a problem with how much time that I have to count for that burn-in phase.
That will depend, you know, on the trace plot. You know, and also on the autocorrelation phase. If your data is still if the samples is still highly varied, then they haven't reached equilibrium. So that's probably you have to discard it.
Okay, thank you.
All right, hope that helps.
Okay, maybe the last question. Is there any question from participants? There is no, maybe the simple question. What is the interpretation about the banana shape or straight shape in a corner plot if we get a shape something like that?
Well, what do you mean? What, the banana shape? It doesn't really have. It means your data is correlated. So if you draw the corner plot, then we draw this pairwise comparison between data. It means there are correlations between these two parameters, as we have seen before in the corner plot of straight line. And that makes sense, right? If we change the slope, we'll change the. Well, it doesn't really look like a banana, but you can see it's correlated, and that makes sense, right? If we change the slope, we'll change the 0 point, and vice versa.
Okay. Maybe the last question from Rafi is okay.
Okay.
Yeah.
Sure.
Am I audible?
Yeah.
Yes.
Yeah, I can hear you.
So you gave assignment, I guess, in the previous day. Actually, we determined the normalized posterior in the parallax. Measuring the parallax, yes. So measuring the distance from the parallax, I guess. So what were we expecting from the normalized posterior? Can you comment on that, if possible? So we
what do we expect?
We used two like priors, and one uniform.
Yeah,
one
uniform distance.
Yes,
Yeah,
one exponential. Would you explain that a bit, if that's possible?
Are you asking what's the point of this?
Yeah,
of,
yeah,
doing,
yes,
of
yes,
doing
yes.
this thing?
Yes,
Yeah. What's
yes,
the point is to compare your results between when using these two priors, and see if they make a difference. That's and that's basically it. If it's the same, if you get the same results, then can you explain why you have the same results? Yeah, I mean, we have two different assumptions about how stars lie, right? In a uniform distance prior, we assume that stars have equal probability to lie anywhere. But in an exponentially decreasing space density, we assume that stars there are more stars, there are more close stars than there are far away stars. So how come these two assumptions explain give out the same result if it's the same now, and why is it different if you have different results? So that's I think the point of this exercise is to see how does prior can affect your results, and to think whether is it actually better or not. That's basically the idea behind the exercise, and also to learn some methods on how to evaluate, how to get the posterior. I hope that answers your questions.
Okay, maybe that one is the last question. So we meet our end here. So yeah, thanks for your great lecture. And then I wanna invite everyone to open their camera and give applause to Dr. Tri. And then we will have a photo session maybe.